Starting a new chapter on electrons and chemical bonding today. Light, as you may know, is a form of radiation. It's a form specifically of electromagnetic radiation. It's not matter, right? It doesn't occupy space. It doesn't have mass. You can't weigh out light on a scale. It's a form of energy, and it travels through the world at a blisteringly fast pace in a vacuum, and really fast pretty much everywhere else. It has properties of waves as well as properties of particles. When a water surface is disturbed, you get waves that radiate outward from that site. So we got this little blop from where a water drop hit. Water spiked up, and we can see all of the little waves that are radiating outward, and those are carrying the energy of that surface disturbance, that water droplet. Light has a similar property, like waves on water, of wavelength. So light we can think of as having oscillating up and down shape to it. Unlike waves on a calm pond or an ocean, they don't usually decrease in size or magnitude as they travel. So one of our properties of light is that it has a wavelength. A wavelength is the distance between adjacent crests or peaks. And we use the symbol lambda, the Greek letter lambda, to indicate wavelength. For visible light, wavelength determines color. So a certain blue color, whatever blue color it might be, is always the same wavelength of light. So if you have a favorite color, it's always going to be that exact same wavelength of light that makes it that color. You might also know from historic music album artwork that white light, if you shine it through a prism, so we've got a glass prism here, we've got light shining into it, and it's refracting out. And because of the way that light behaves when it enters a material, those beams of light slightly separate out, and so you get this nice rainbow color that comes out. You can also see this sometimes in your house. When light comes through a window at just the right angle, it'll spread out into a small little rainbow on your wall. This also happens to form the rainbows that we see when it rains. The water droplets act like prisms and deflect the light a little bit each time it passes through, resulting in a rainbow. Another important point about light, plants appear green, generally. Most plants look green. And that's because the chlorophyll molecules absorb blue and red, and they reflect green light. So the color you see is the reflected light. There are occasionally sad stories of people that buy green lights for their plants to try to give them energy and help them feel happy and live long and prosper inside their house. And so they're giving them the one color of light or one of the colors of light that just bounces off. They don't absorb it at all. And so even though you're maybe giving your plants a lot of light, it's not the light that they need. It's not the blue and the red that they need. And so all of that light just gets reflected, and the plants don't end up living very long. Obviously, on this plant, we've got a little bit of red around the edges, and so those parts, for whatever reason, are instead reflecting red light rather than green light. A related physical property, physical property of light is frequency, with the Greek letter, I'm pretty sure it's nu. So the frequency is how many cycles or crests. So if we're thinking of our waves as traveling, right, that up and down motion, if we lock those up and downs and we just kind of laterally transfer them, move them around, how many of those cycles, how many of those peaks are passing through a checkpoint basically at any given time, specifically in 1 second. So as you can maybe imagine, let's draw out. There's like a really long wavelength. And let's draw out a shorter wavelength. So if both of these wave patterns are moving left to right at the same speed, on our top long wavelength, it's going to take a longer amount of time because we've got further distance between our peaks. It's going to take longer for those peaks to pass through off the right of the screen, versus this short wavelength, we're going to get more of these peaks passing off the right of the screen if they're moving left to right. So long wavelength low frequency. We're not going to get very many of these peaks passing off the right side of the screen in a given amount of time because they're so separated. For our short wavelength, we're going to have a high frequency. So one of these values, as it gets smaller, makes the other bigger. And that's what we call inversely related. So that's the wave part of light. Light can also be viewed as a stream of particles, like little tiny atoms or something. And our smallest unit of light is a photon. A photon is just a single piece of light, a single packet of light. It's the smallest amount of light that you can get. For those little packets of light, they also still have that wave energy within them. So wavelength plays a role, frequency plays a role. It's all tied up in that little packet of light. The amount of energy in that piece or packet of light depends on the wavelength. Short waves mean high frequency. And high frequency is high energy. Hopefully you've all been to the beach. If you've been to the beach on a nice calm day, the lovely sound of the waves rolling in, nice and slow, very calming, very relaxing. If you've ever been to the beach on a stormy day, waves coming in maybe not so slowly, not so calmly, a lot more waves. The more waves, the less peaceful it is. And that's a similar idea with our short wavelengths. If you've got a lot of waves coming in rapidly, that's kind of chaotic, not really great for reading a book on the beach, compared to a long, low frequency where you get nice calming waves on the beach. Do we have questions about light so far? Confusions about light? Okay. If you just want to memorize the relationship, there's kind of your two relationships, long wavelength, low frequency. So you could also think high wavelength, low frequency, low energy, low wavelength, high frequency, high energy. And then this little cutout that we've got, this is all of the electromagnetic spectrum. On the top, we've got increasing frequency moving from right to left. So hertz is the unit of inverse seconds, or 1/seconds, or per second. So how many waves per second? So on the very far right side, we've got 10 to the 0, which is 1. So 1 wave per second, very, very slow, very low number of waves. On the lower side of this, we've got increasing wavelength moving left to right. So on the very far end of this spectrum, we've got 10 to the 8 meters, an astonishingly long distance. Really, really, really long wavelengths. And radio waves correspond to this very long wavelength and very low energy, very low frequency section of the electromagnetic spectrum. That's part of why we use radio to listen to the radio. It's these really long wavelengths. They travel very long distances without decaying a ton, so that works out really nicely. And AM travels longer than FM. If you haven't listened to AM or FM radio, it's just the way it works. You can get AM radio from like Texas, even out in California. And then we've got a bunch of other sections. And we've got, of course, the visible spectrum, this tiny little cutout that we can see with the cones in our eyes. Cones see color because they're pointy. And notice something about the spectrum. What's the order of the colors in the spectrum? It's a rainbow. Colors are in rainbow order. That will be helpful. All right, let's go through and talk about some of these parts of the electromagnetic spectrum, or the light spectrum. All the way on our highest energy side, we have gamma rays. Gamma rays have the shortest wavelength and are the most energetic. They're produced by the sun and stars. And some unstable atomic nuclei on Earth also produce gamma rays. Gamma rays are really bad for you, great way to get cancer. Fortunately for us, we have an atmosphere that protects us. Or it might be the magnetosphere. That protects us from a lot of that radiation. if I'm remembering correctly. So part of the reason why it would be tough to go and make a colony on Mars, Mars does not have an atmosphere, might have a magnetosphere. And so we would need some extra protection in the form of some of those chemicals that are up in the atmosphere. Or we would have to wear really big Martian suits. Then slightly lower in energy are the X-rays. X-rays, as you probably know, pass through solid substances. Great for taking pictures of teeth. Great for seeing bones, since bones tend to be more dense than the rest of our flesh. X-rays, though, are still really high energy. So it's not a great idea to be getting X-rays all the time or being exposed to X-rays all the time. If you've gotten your teeth X-rayed at the dentist, you may have noticed they put a big lead apron on your body. That's to protect your body from the X-rays. And then they step out of the room, press a button, you hear the little beep, and then they step back into the room. We'll call them dental hygienists. That's probably not all of them. Most of this is just like fun flavor for you. It's not like stuff that I'll test you on. The stuff I'm writing in, that is. So dental hygienists step out of the room for X-rays to reduce their exposure. Since dental hygienists are doing X-rays probably every single day of the year that they're working, if they were in the same room as you while you're getting your X-rays, that would expose them to more X-rays, which would lead to higher cancer rates, which is how it used to be. So there's problems that can arise from getting too many X-rays. When you're going to the dentist, once a year for your X-rays, hopefully you're doing that, it's not really that big of a deal. All right, and then below that in terms of energy is our ultraviolet light. So ultraviolet light is also high energy. It produces a sunburn or a suntan, depending on what sort of genetics you have. They're less energetic than X-rays, but still, as you have definitely experienced if you've gotten a sunburn, damaging to biological molecules. As the name implies, ultraviolet, they're right next to violet. They're higher than violet light, and specifically in terms of energy. Ultraviolet light, right, is responsible for sunburns. It's got a lot of energy. You know that it's got a lot of energy because it hurts you if you get too much of it. It's right next to violet on the visible light spectrum. Visible light does not damage biological molecules, but it does cause molecules in our eyes to rearrange, resulting in vision. Cones see color because they're pointy. That's one of my takeaways from freshman biology, at least. And we talked about visible light. It goes in the rainbow order. Of colors. The UV light, being high energy, is right next to violet. So violet is going to be our high end of the energy for visible light, and then it'll decrease in energy all the way down to red. There's another way that I think is really helpful for remembering the order of visible light and the wavelength. When you see a rainbow, what's the outside color of the rainbow? Like what's What's the top of the arc for a rainbow? Red. Our top of the arc is red, and then we proceed in color order. I'm missing a few. We proceed in color order all the way down to violet. If you're running, hopefully you all have run on a track. If you're running on a track or if you're driving on a race course that's got a turn in it, which of these colors, if these were tracks, would you want to be on if you're racing someone? You'd want to be on purple, right? Because it's the inside track, it's the shortest track, it's the shortest line. Conveniently, this also tracks with wavelength. Red is the longest and has the longest wavelength. Purple has the shortest wavelength. And everything in between just runs in Roy G. Biv rainbow color order. So that part, not really flavor text, that is actually helpful because I usually put an exam question about that. All right, moving on past visible light. Just next to the red side of the visible light spectrum is infrared light. As the name implies, it's below red. It's right next to red. On our visible light spectrum, infrared light is what you feel when you place your hand near a hot object. Hot objects emit infrared light that we feel as heat. And infrared or IR cameras can be used as one form of a type of night vision technology to see in the dark. You'd have to get a lot of infrared light, a lot of infrared radiation, like from a heat lamp or something. You'd have to get a lot of it for you to actually get damage. It's generally fine for you to feel you're emitting infrared light. For the most part, it doesn't damage you. Not like UV does. UV will burn you. IR generally doesn't burn you. So that would be another way that you can remember your order for the visible light spectrum. Ultraviolet right next to violet, lots of energy. Infrared right next to red on the visible light spectrum, not a lot of energy. Some of you may also be familiar with laser pointers. The historically most popular color for laser pointers is what? Red. Why would it be red light? There's less energy. Is a big part of it. We also see red really well. Green laser pointers often look a lot brighter. I think we see green a little bit better than red. But it's also higher energy. If you shine it in somebody's eyes, you're more likely to do damage. Violet laser pointers are really dangerous because they're hard to see. They're also really high energy relative to how well you can see them. So red laser pointers are nice and easy, less chance of damaging somebody's eyes. It's also just a classic. Here we've got a very cool infrared photograph. So in this infrared photograph, we've got an overlay of just a picture of this plane on the left for this far right image, and then the infrared photograph on the right side, where our warm areas are this red and the cooler areas are that dark blue. So that's an image of the shuttle orbiter Columbia returning to Earth back in 1982. And that picture was taken from the Kuiper Airborne Observatory, which I believe is this one. So they took a picture of a space shuttle from a plane, which I think is really cool. I just think that's a fun application of infrared. And then below infrared, we have microwaves, like are used in, of course, radar, which makes not a whole lot of sense to me, and microwave ovens also use microwaves, as the name implies. Microwaves are really efficiently absorbed by water, just because of the way that they are. The bonds in water pick up those microwaves really well, and so that causes things that have water in them to heat up if they're exposed to the correct wavelength of microwave energy. The reason that microwaves being used for radar doesn't really make sense for me is because radar means radio detection and ranging. So it seems like that should be radio waves. But anyway. And then our lowest form of energy for the electromagnetic spectrum is radio waves, like the old AM and FM radio, our phones, television, lots of other forms of communication. If you need it to go a long way, radio waves are the way to do it. So those travel long distances well in comparison to the other bits and baubles and pieces. All right, testing your knowledge about the visible spectrum. Please arrange the colors of visible light, just green, red, and blue, in order of increasing wavelength, frequency, and energy per photon. And we'll come back together and go over that in a little bit. All right, wavelength for our colors of light. There's a strategy that you can employ on a question like this. What's the order of these colors? Green, red, and blue. Just give me an order that they would show up in the rainbow.
Red.
We'd have red. What would come next? Green. And blue. So that could be one of our orders. Another order that we could have is the opposite. We could have blue, green, then red. If you're asked a question about which of these three colors has the longest wavelength? There's one of these, even if you don't remember anything else, there's one of these that you should never pick. If we're asking about the longest or the shortest, which one should you never pick? Green, because it's the middleist color, right? If we're asking longest or shortest, any sort of longest or shortest question, or highest or lowest, green's in the middle. It's not going to be longer or shorter or whatever than the other ones. So if you're asked a superlative question, don't pick green unless we don't have, something outside of it like blue or red. That being said, for wavelength, what is our shortest wavelength of light for these three? Blue. Blue is more inside on our rainbow, and then slightly more outside that, and the most outside that would be red. So blue, green, then red. So blue has a shorter wavelength than green. Green has a shorter wavelength than red. And how about for frequency? What's our relationship between wavelength and frequency? They're opposites. So long wavelength equals short or low frequency. Yeah, we'll write low instead of. So low frequency. So our order is going to be flipped. So red is going to be our lowest frequency. Up next, green, our middleist color, and then blue. Blue is going to have the highest frequency. Because it has those short wavelengths. And then for our energy per photon, which of these colors is going to have the least energy per photon? What's the lowest energy light? Red. It's red. Red has our lowest energy. It's right next to infrared. Red also used in laser pointers because it's low energy. And then we proceed in rainbow order. So we go to green next, and then lastly, blue. Blue is closest to violet of these three colors, which is next to ultraviolet. Which causes sunburns. High energy. There's a couple of ways of remembering the color orders, so hopefully one of those sticks with you. Questions about any of those? All right, getting into our atoms. What do atoms look like? We've got models for what atoms look like. It's hard to see an atom because they're really small. Our eyes don't do well with looking at things that small. They also move around really fast. So we'll start by talking about our Bohr model, named after Niels Bohr. You may know that neon atoms, if you put them in a glass tube, and you give them a lot of electrical energy, they can turn that energy into light, like neon signs. Neon signs, as you may know, come in lots of different colors. You can do the same thing with other elements. So it's not just neon. Neon being our second noble gas, number 10 on our periodic table. It's just that neon's the most popular one. You can also do it with a mercury lamp, very dangerous. And you get a fun lightsaber blue color. You can also do it with a hydrogen lamp, and that emits more of a pink color. Those light wavelengths, the colors that you see, are very distinct and specific to the element. So if we zoom in on a light spectrum emitted by hydrogen, this is what it would look like. So we've got this one red band, we've got a light blue band, we've got a darker blue band, and we've got a purple band kind of far over to the left. Some of those don't show up real well on the projector. So these are wavelengths that would have been separated on a prism and then captured on some sort of film so that you can see the individual colors of light. Notice that there's a giant empty space between this red and the light blue. There's a slightly smaller space between the light blue and the dark blue, and there's an even smaller space between the dark blue and the purple. But we've got big stretches of empty space. It's not a continuous spectrum like we see with white light. Right, so for a white light spectrum, what we expect to see, if you send light through a prism, it's got all of the colors, it's continuous. There's no gaps in our white light spectrum. In our hydrogen and helium and iron emission spectra, we have just individual lines, singular wavelengths, and then lots of little gaps in between them. So these are examples of emission spectra. There's Go away, Siri. What the heck? My watch is going crazy, and it was Siri trying to listen in on something. So there's only specific wavelengths that are shown with big gaps in between them. You might also notice another trend when we move from hydrogen, hydrogen being our smallest atom, up to helium, we get noticeably more lines. And they also don't exactly line up, right? We've got slightly different colors for each of these. We don't have exactly the same blue overlap. We don't have the same dark blue overlap. And we get more colors the bigger our elements get. And this is something that Niels Bohr and others noticed when they were creating these light spectra. They wanted to know, why are we seeing only specific wavelengths of light? Niels Bohr came up with a model to try to explain this. So our atoms have a nucleus. That's where the protons and neutrons are. Electrons in the Niels Bohr, the Bohr model, orbit the nucleus. On fixed tracks. They're not exactly tracks, but they are a set of concentric circles. So our nucleus here, this dot in the middle, and then we've got orbits with different levels. The closest orbit, the closest track, we can think of like our solar system model, right? Planets orbiting the sun. Our closest is n equals 1. We jump out to n equals 2 for our next orbit, and 3 and 4, and so on and so forth, for however many n levels you want to get. So we would have, maybe we'd represent them as dots for electrons that are traveling around on these orbits. They're fixed on that track. And the way that Bohr proposed that we get these specific wavelengths of light is that part of the Bohr model, these tracks are fixed in terms of their distance to each other. They're fixed at a specific distance. So if we have hydrogen, our n equals 1 level is always going to be the same distance from our nucleus, and that's going to have a certain amount of energy associated with it. Quantized is another way that we can talk about it. And so our orbits are specified. We refer to them by their quantum number. That's just the n. So fixed levels with fixed spacing. We can't have electrons that exist in the space between them. And since they're fixed at a specific distance, and therefore a specific energy, then that means that when we move between those energy levels, those quantum levels, those orbits, there's a fixed amount of energy responsible for that change, for that difference. So the fixed distance between orbits equals a fixed energy level, or energy difference, rather. And each of our atoms is going to have electrons that show up in some of these different orbits. Those orbits, those electrons in the orbits, can absorb energy of light and jump up to a higher orbit level. When they do that, they don't want to stay there forever on that whatever orbit track they're on. Eventually, they will relax, as we call it, and they'll drop back down to a lower energy level. So we're seeing that for this green dot moving over to this other green dot. We've got an n equals 2 electron dropping down to an n equals 1. And since this distance is fixed, when it releases that energy corresponds to a specific wavelength of light that it emits as a photon to get rid of the energy. And sometimes that light shows up in the visible spectrum. So every n equals 2 to n equals 1 jump will release the same energy, the same light. So that's why we see those fixed intervals on our emission spectra. Those correspond to jumping between these different energy levels. Questions about any of that so far? Great. We'll pick up here next class.